start the old recording here. Go back here. Oh. We like to do things in the dark. That. Okie dokie, artichoke. There we go. So, like I said, I've moved everything to Moodle because I've had to give up on Slack. Right, and so on Moodle, there's just a permanent meeting room that's always open. Right, so that's where I'll have all my lectures. Right, so you can just, well, you can come into business math if you want to. Not sure why you would want to, or I understand why you would want to. That's what I should be saying. Right, but so the link to our permanent online meeting room is posted on Moodle. Right. Thanks. Or you can join 250-864-8386 is the meeting room, but also my phone number. So because we're migrating away from Slack, I do want you to have an easy way to message me. So you can just text message me. The reason I was kind of avoiding it is because it's not because I don't like it. I actually prefer to text than email. I don't know about you guys. Email just feels, it's the same thing, but it just feels a little bit more tedious for whatever reason. So I do like texting. It's just hard to keep track of who's who. And so if you're sending me a text, maybe start it off with, hey, this is blah, blah, blah. And then we can go from there, okay? Because I have so many chains where someone hasn't actually revealed who they are. And who might ask, right? So, also my phone number. Feel free to text. If you have questions. So I was trying to set up a separate stream where we message. That didn't work out. I'll try again next term. I'm nothing if not stubborn, so. Okay, but for this term, we'll just do it the old way. People seem to like to text me. I think it's, but yeah, so feel free. Okay, so last day we started probabilities, right? And we talked about some probability facts, right? So just as a quick review, and we're gonna go through examples today. We didn't get to any examples, right? We just talked about all this stuff that I'm expecting you to know, right? So for review, oh, you know what? Before I start the review, I just want to clarify that there is no lab due on Friday. Not sure what happened there. Okay. No. There will be a lab going over lab 2 on Friday. Thank you. Worth clarifying. Okay. So there's no lab 1 due on your term schedule, right? we said that the lab 1 was due on Friday. There is nothing due for lab 1. So, right, as long as you've gone through, and I did post that video, right? Lab 1 video posted on YouTube. And all the videos should be posted. You might have to just search all my videos because I think it only shows a highlight reel. I'm not sure how it picks those, but right. So all the videos are posted on there, and the lab 1 video just ended up being a quick and dirty 20 minutes, right? When it was just me and I in front of the computer, ding 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 ding. Okay. So. So if you want a recap of lab 1, right, I am assuming that you know that stuff from now on. Okay. Now we can do our review. Hopefully everyone's handed in their assignment.
I sent it to you on my phone actually 5 minutes before.
Okay.
But I can't read it.
No, it's fine. Yeah, I'll take the hard copy. I always prefer the hard copy because usually what ends up happening is, well, now I'll try marking it on the iPad, but usually I have to print it off if you scan it to me and email it to me. So I always prefer the hard copy.
I know. But you said after 8
I
o'clock, you're like,
No, you're good. Don't worry.
It's on erasure.
I know. That's good. It's good. It's good. So just a quick review. Right, we said that, okay, now we're talking probabilities. Probabilities have 2 main characteristics, right? So probability facts. Probability facts. First one, and I'll just use the shorthand that's on your formula sheet, right? Because we defined it last day. All probabilities have to be between 0 and 1, right? That's on your formula sheet. And the total probabilities, right, the sum of all possible probabilities for an outcome or for an event has to equal 1. Okay. And then we talked about valid probability distribution. Valid probability distributions. Right? We said that each outcome must be discrete, right? The probability distribution was a table of all possible outcomes with each of their probabilities listed below it, right? And so we went through an example, and on the test I'll ask you, is this a valid, or pick the valid probability distribution, right? So first thing we're gonna check is that each of these outcomes have to be disjoint, right? Meaning that they can't have overlap. So each outcome must be disjoint. Right? We talked about disjoint. Disjoint meaning no outcomes in common. Right? And then we check that each probability is between 0 and 1. And then finally, if an option checks out on both those counts, then we make sure that the sum of the probabilities is 1, right? So then we check that the sum of the probabilities is 1. Then we went through and we developed the formula that the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. Okay. Thinking back to that set of cards or the deck of cards that was laid out, right? We had our diamonds and our face cards, and then we had to subtract that overlap, right? Because the 3 face cards that are diamonds would have been counted twice, right? And that's the minus probability of A and B. just subtracting that one layer of overlap. Okay. And if A and B are disjoint, then the probability of A and B must be 0, right? Thinking back to, okay, what does it mean to be disjoint? Well, it means that there are no outcomes in common. What does that mean in terms of a probability? It means that, well, the probability that they happen together is 0, right? Which lets us develop that special case of the probability of A or B just being probability of A plus the probability of B. Okay. Then we talked about independence, right? Independence is different from disjoint, okay? Independent, so two events are independent if the outcome of one does not affect the probability of the other. Okay? So if the outcome of one does not affect the probability of the other. Right. And so we have a pretty good idea of independence. Right? If I told you that, it's supposed to be snowing and miserable out tomorrow, you'd say probably not, right? Just because weather is not independent. So just because we consider today and then we say, well, that's very unlikely, right? Because we know that the weather tomorrow is sort of, unless you live in Alberta, I guess, sort of linked to the previous day, right? And the day before that, and the day before that, right? And so we went through some examples, but now, end of the review, I want to show you how do we calculate if two events are independent. Okay, so as a fact, any questions before we kind of keep going? I do have examples for you, but we got to cover all this stuff first. All good. So as a fact, two events, A and B, are independent if and only if, and only off, yikes. It's because in math we write if and only if as IFF. I wrote off. So if and only if the probability of A and B, can't write at all today. Probability of A and B is the same as the probability of A times the probability of B. There it goes again. Okay. This is not how we find the probability of A and B, right? We're saying that this equation will only be true if A and B are independent, right? So we can't assume that two things are independent and just use that to calculate the probability of A and B, right? When might we need the probability of A and B? Well, up here in this formula, right? If we're calculating the probability of A or B, right? So it might be tempting, but this formula is only for us to use if we're checking to see if A and B are independent. Right? So we can't use them the other way around. And it's on your formula sheet, which I forgot to bring. Oh well. If you need a copy, you can follow me to my office later. Okay. So two events are independent if we can show that the probability of A and B is the same as the probability of A times the probability of B. Okay. So, where was I here? Oh, here we go. I'll just say, so same idea, if the probability of A and B does not equal the probability of A times the probability of B, A and B are not independent. Right. Same thing, but just different wording. Let's steal an example here. I'm going to go back and steal this. And you know what? I'm going to keep the little girl with her A. Okay. So here's an example, probably a little bit more involved to figure out the probabilities than what I would expect, right? But it's a good place to start. So in a math class of 30 students, 17 are boys and 13 are girls. On a unit test, 4 boys and 5 girls made an A grade, so they got an A. If a student is chosen at random from the class, what's the probability of, and so the first thing we're gonna find is choosing a girl or choosing an A student, right? So what I would do, right, we essentially have, I guess, four things that we've talked about, right? We talked about just picking a girl, right? And just picking a boy, picking a girl who got an A, picking a boy who got an A. Okay? We can talk about it as 3 things too if we want to. Okay? So let G be choosing a girl, right? In your random sample, we're going to denote just picking a girl as G, right? Just shorthand. And let A represent choosing an A student. Okay. So we'll narrow it down to just either it's a girl or the opposite would be a boy, right? We talked about the complement, forgot to mention it in the review, right? But the complement is just the probability of not happening, right? Or the event of not choosing a girl is choosing a boy, right? And so the first question, we want to know what's the probability of choosing a girl? So the probability of choosing a girl is going to be, so there's 30 students and 17 are boys and 13 are girls. So 13 out of 30 are girls. And that's how we find that probability. So 13 out of 30. Or if you prefer, we can use the decimals. I don't know about you guys, but I'm not a huge fan of fractions. 13 divided by 30, or 0.433 repeating technically. Or choosing an A student. So the probability of A, right, because we said A was choosing an A student, how many of these got A's? 4 boys and 5 girls. So just in general, out of all 30 students, right, 9 out of 30 got an A. So there's lots of probabilities that we could talk about, but we're asked to find these, so that's what we're doing. 9 divided by 30, or 0.30. So far, so good. Cool. Second one, what's the probability of choosing a girl who got an A on the test? So we can write that as the probability of choosing a girl and an A, right? Because they have to happen together. So now we're only talking about the girls and those who got an A, right? And so 5 out of the 30 students were girls who got an A. So it's 5 out of 30. Or 0.167. 0.16 repeating, but we'll round it. Good. Now we want to know what's the probability of choosing a girl or an A student, right? So we can either pick a girl, right? That's any of the 13 girls, or any of the A students, which includes the 4 boys who got an A as well, right? The 5 girls who got an A, they're included in the 13 girls, right? These aren't like super girls, they're just A girls, right? And so they're still counted in that girls category, right? So if we write it out in notation, it's actually easier to look at. We want to know what's the probability of choosing a girl or an A student, so a G or A. And from our formula sheet, right, we know that this can be written as the probability of G plus the probability of A minus the probability of G and A. So if we're solving for this, right, we already have the probability of G, we have the probability of A, and we also have the probability of G and A. Wow, it's like I'm just walking you through all the work. And that is how it will be, so don't worry. Okay. So the probability of G, we said, was 0.433. If you work with fractions, that's great. I wouldn't worry about it, right? If you want to convert it to decimals, stick to maybe 3 decimal places, 3 or 4. Right? If it's important, I'll tell you how many decimal places to keep on the test. Okay. The probability of A, we said, was 0.30 minus the probability of G and A. Remember, we have to subtract the girls that got an A, right? Because we would be counting them twice, right? So minus 0.167. So we have 0.433 plus 0.3 minus 0.167. I get 0.566. So in general, right, with this equation, the probability of G or A, right, we have essentially 4 terms, right? So if I give you 3 of those, I can ask you to solve for the 4th one, right? It doesn't always have to be the probability of G or A. I might give you the first 3 and ask you to solve for the probability of G and A, for example. Okay. How about the last question? Are choosing a girl and choosing an A student independent? Right. So does knowing that you picked a girl tell you anything, or does it change the probability of them being an A student? is essentially what we're asking here, right? But if I'm asking, are these two events independent, we know that we have to show it mathematically, right? And so hopefully you have your formula sheet, right? But we know that G and A are independent if and only if the probability of G and A is the same as the probability of G times the probability of A. Right? So we're checking to see if this is true. So what I like to do is I like to throw a question mark over top. You don't have to, but right, just to remind myself that I'm just checking, are these two things equal? Right? So we said that the probability of G and A was 0.167. Is that the same as the probability of G, which we said was 0.433, times the probability of A, which we said was 0.30? So now we can calculate these and say 0.433 times 0.30 is 0.1299. Even if it was because of the rounding, right? Those should be pure fractions, right? I've rounded 0.4333 repeating, right, to 0.433. But even if I'd kept them, it wouldn't matter, or they wouldn't be the same. And so 0.167 is not equal to 0.1299. Here's the thing, they have to be exactly the same for it to be true, right? So even if we got an answer of 0.168, right, then you would want to check to make sure that it wasn't a rounding thing, right? But if you've checked all the rounding and stuff and you get 0.167 is what it's supposed to be, does it equal 0.168? No, it doesn't. 0.167 only equals 0.167, right? So since the probability of G and A does not equal the probability of G times the probability of A, we know G and A are not independent. Not independent. I don't know why, but I don't call them dependent. I just talk about being independent or not independent. Of course, not independent is dependent. So if you want to use that, that's fine. But I just like to stick with independent, not independent. Just terminology.
That would make you more likely to have an A.
Well, it looks like it from the data, right? But all we're saying is that if you're a girl, that affects the probability that you have an A, right? And it looks like the probability is higher, but all we can say is that the probability is affected. We can't say which way yet. But looking at, 5 out of 13 or 4 out of 17, yeah, it looks like it's higher, right? So you can hypothesize that, but we can only talk about just in general the probability. Any questions? No? How about another example? I can't remember where I stole these from, these examples, but I remember deciding to keep the images because I think they're really cute. And my slides are typed up in LaTeX. I don't know if anyone uses LaTeX, probably not. Which means that importing the images is a little bit more work, but I'd say it was worth it. Look at this guy. me see. He's crashed his car. Let's call this example 2. Sorry, it pasted a little bit lower, but. Okay. So on New Year's Eve, the probability of a person having a car accident is 0.09. I guess I was sloppy typing up. The probability of a person driving while intoxicated is 0.32. And the probability of a person having a car accident while intoxicated is 0.15. Okay. Yikes. So first thing we're gonna do, and first thing we're asked to do, but would probably do anyways, right, is list the 3 probabilities given using probability notation, which means we're gonna define all 3 of these probabilities, right, because there's 3 probabilities given. So we have to define each of the events, right, in terms of a variable, right? Just like we said, let G be choosing a girl and let A be choosing an A student, right? We're gonna say that well, what are we talking about here? Let a car accident, let's call it A. There's a lot of A's around here. It's fluky. Let A be a car accident, right? Or denote a car accident. And then we're told that the probability of a person driving while intoxicated is 0.32. So the other thing that we're going to talk about is whether someone is driving while intoxicated or not. So driving while intoxicated. And then finally, we're told, and the probability of a person having a car accident while intoxicated, that's just A and I, right? So we've defined the 2 events that we're talking about here. So the first point, list the 3 probabilities given using probability notation. So we're told that the probability of having a car accident, A, is 0.09. Then we're told that the probability of driving while intoxicated is 0.32. Yikes. And then finally, we're told that the probability of a person having a car accident while intoxicated is 0.15. So the probability of having a car accident while intoxicated, so that's and, right, because they both have to happen at the same time, we're told is 0.15. So far, so good. Okay. So this is probably more likely what I would give you on the test, right? List some things with some probabilities, right? Not the 5 girls got an A, whatever, right? Okay. So question 2, are having a car accident and driving while intoxicated disjoint events? Right. So now we have to think back, okay, disjoint events, that means that they can never happen together, but we just wrote down that the probability of having an accident while intoxicated, right, them happening together, is 0.15, right? So we can justify this and say A and I are not disjoint since the probability of A and I, right, the probability of them happening together is 0.15, which is not 0, right? If two events are disjoint, they can never happen together. So the probability of them happening together must be 0. So I want to see some mathematical justification for that question, right? Are they disjoint? Then you look at the probability of A and B in general. And if it's 0, then yeah, they're disjoint. If it's not 0, they're not disjoint. How about question 3? What's the probability of a person driving while intoxicated or having a car accident? Right, it's possible to have a car accident without being intoxicated. Right? It's possible to drive intoxicated and not get in a car accident, right? So we're just talking about either one of these outcomes. Okay? So we want to know what's the probability of A or I. And from your formula sheet, you know that that's the same as the probability of A plus the probability of I minus the probability of A and I. So we're trying to find the probability of A or I, right? And we know all the other 3 terms, right? We know that the probability of A is 0.09 from up there, first part. The probability of I is 0.32 minus the probability of A and I is 0.15. So we get 0.09 plus 0.32 minus 0.15, 0.26. Cool. Question 4. Are having a car accident and driving while intoxicated independent events? We know how to do this, right? We just covered it. And so we're going to show it mathematically, right? By seeing if the probability of A and B is the same as the probability of A times the probability of B, or I guess B is I in this case. So A and I are independent if and only if the probability of A and I equals the probability of A times the probability of I. So we want to know, is that true? The probability of A and I, we know is 0.15. And we want to see if it equals 0.09 times 0.32. 0.09 times 0.32 is 0.0288, which is not the same as 0.15. So we say that since the probability of A and I is not equal to the probability of A times the probability of I, we know A and I are not independent. Oops. Oh my goodness. The screen keeps jumping around. Okay. Cool, nice work. Any questions about those?
Okay, so just to clarify,
Mhm.
so disjoint means that the probability of A and I have to equal 0.
Yeah.
And then, so for example, like blank and blank are independent only if the probability of the blank and blank minus the probability of blank, they equal each other. Correct.
Are you talking about this one? The
Mhm.
probability of A and I has to be equal to the probability of A times the probability of I. Yeah. True. And on your formula sheet, those should be on there. Can I just see this one? Thanks. Right. And so you have, we skipped one equation, right? We're going to get to it. But the probability of A or B, right? We have that equation. And then we say if A and B are independent, then the equation that follows is true, right? So it's on there. You just need to know how to use it. Thank you. Okay. All right. So we're going to get into section 2.2, which is on conditional probability. Conditional probabilities come from, if I say, I know I picked a girl, what's the probability of picking an A student, right? Talking about that previous example that we kind of started with, right? Or I know I have someone that was in a car accident, right? So just kind of narrowing down the sample that we're interested in, right? I know I have someone that was in a car accident. What's the probability that they were driving while intoxicated? That probability is going to be changed because now I've narrowed down my search essentially to someone who had a car accident, right? And so now we have conditional probabilities, right? Conditional on someone having a car accident, right? We know that already about them. What's the probability of them driving while intoxicated? Okay. So I'll steal an example. Oops. It's because I just snapped a picture of the textbook. The textbook? Yeah, I know. I haven't even cracked that thing. I know. It's okay. I'll crack it for you. Like I said, I'm not going to be using the textbook too much, but I do steal examples out of it. Sometimes even questions, assignment questions. Now you know. So, okay. So the family college data set using, so this textbook uses R in their calculations and things like that, right? So when we see kind of this, I don't know, the family college, right? Family_college, we know that's R code, right? It's not R code, it's just telling us what it would look like in R, right? So the family college data set contains a sample of 792 cases with 2 variables, okay? Teen and parents, okay? And is summarized in table 2.11, whatever, the one I stole below. So the teen variable is either they went to college or they didn't go to college. Okay? Where the college label means that the teen went to college immediately after high school, right? Or they didn't. Right? You can go to college later, but you would be considered as you didn't go to college immediately after high school. Right? So the parents variable takes the value degree if at least one parent of the teenager completed a degree, or a college degree, I should say. Right? And so you have, did this teenager, did they go to college right after high school? Yes or no? right? And the parents of each of these teenagers, right? Does at least one of them have a college degree, yes or no? So now we have these contingency tables, is what they're called. Okay. So this is a contingency table. I guess I can just underline it. Okay. So we said we have 792 cases, right? So this here is the total, the 792. And if we wanted to know just how many teens went to college right after high school, right, then we would go and say, okay, the college, I don't care if the parents had a degree or not, right? The total teens out of the 792 that went to college right away is 445. Okay. Or we can talk about how many teens didn't go to college right away, but their parents have a degree, or at least one of their parents has a degree, right? So now we can narrow it down and say, okay, didn't go to college, so not, and then have a degree, their parents have a degree, so 49 out of the 792 total students didn't go to college right away, even though one of their parents has a degree. Okay, so doing the same thing that we did before, right? I'm just gonna define my variables so that I can just talk about each of these events as a variable. So either they went to college or they didn't go to college, right? So I can talk about college, or either the parents have a degree or they don't have a degree, right? So let C be that the teen went to college immediately after high school. We don't want to be writing that out 10 times over, right? So we just say C, right? They went to college right after high school. And we can let D represent that at least one parent has a college degree. At least one parent has a college degree. Okay. So let's do a little example. What proportion of parents, where at least one, right, completed a college degree? What proportion of parents completed a college degree? Technically, it's what proportion of teens had parents where at least one had a college degree, right? But for the sake of not writing so much, proportion is a probability, right? Remember, those 3 P's are all the same. Proportion, probability, percentage is essentially the same as all of them. Right? So all those 3 P's can be used interchangeably. Right? So the probability of D is what we want to find. So looking at our contingency table, right, we know that if we're just considering how many parents have degrees, then 280 total, right, out of the 792. So the probability of D is 280 out of 792. Yes.
For 280 do have a degree?
Of the parents, yeah.
I'm confused with the teen and the not part. Like that.
Oh, so the 792 is actually referring to how many teens we surveyed, right? And so 280 of them said, yeah, one of my parents has a college degree, right? So it doesn't matter if they went to college right after high school or not, right? We just want to know what's the probability of D. Probability of D is 280 over 792. Let's have a look at another example. If at least one parent completed a college degree, what is the probability the teenager or the teen will attend college right after high school? So now we're getting into these conditional probabilities, right? So if I tell you that, okay, as a fact, the group that you're looking at least one parent has a college degree, right? So we're only looking at these 280, right? Because I'm telling you, given this information that at least one parent has a college degree, then what's the probability that the teen goes on to go to college immediately after high school? Right. So here's some new notation. The probability of the student going to college given that the parent has a degree. And so the given, right, we need some shorthand for given. So we write that as the probability of C and then a straight vertical bar given D. Right. So that means given. And just by looking at our table, right, we know that, okay, if we're given that the parent has a degree, then that narrows down our sample to 280, right, or our total is 280. And 231 out of the 280 went to college right away. Right. So the probability then is 231 out of 280. If you've had a glance at your formula sheet, right, you know that we have a formula for the probability of A given B, right, but we'll work into it. What about another example? A teen is randomly selected and she did not attend college right after high school. What is the probability? What is the probability? I'll just say prob. That at least one of her parents has a college degree. At least one of her parents has a college degree. Question mark. Okay. So now, right, we can look at our contingency table again. Right? Now we're looking at all the teens that didn't go to college right away. That's 347. And what's the probability that at least one of our parents has a college degree? Well, there's 49 out of the 347. So we can write this as, so let's write this in probability notation. So what's the probability that the parent has a degree given that the teen didn't go to college, right? So that's C, the complement of C. C is them going to college right after high school, right? The complement of C is just them not going to college right after high school. Right? Got a little involved, right? But we said that, well, just from our contingency table, we know that that's 49 out of 347. 49 out of 347. Which is roughly, if you want a decimal, 0.1412. So let's talk about some definitions. Okay. So we have these totals, right, out in the margins, right? These totals and these totals. So we call those marginal probabilities, right? A marginal probability is just what's the probability that the teen went to college? 445 out of 792. What's the probability that they didn't go to college? 347 out of 792. The probability that the parents have a degree, 280 out of 792. Don't have a degree, 512 over 792. So those ones in the margins are marginal probabilities. Okay. So marginal probabilities are probabilities based on a single variable without regard for any other variables. Without regard for any other variables. Made me think of that honey badger video. You guys seen that? For any other variables. If you haven't seen the honey badger video, you should probably watch it. So that would be the probability of C, right? The probability of not C. The probability of D. And the probability of not D. all those ones in the margins. So just kind of stealing these here. Grab it. I'll just tell you that it's 445 out of 792. The probability of not C is 347 out of 792. The probability of D is 280 out of 792. And the probability of not D is 512 over 792. Okay. So those are our marginal probabilities. Okay. How about our joint probabilities? Joint probabilities are going to be the probabilities in the center of the table. Okay. So joint probabilities is a probability of outcomes for two or more variables. We'll only talk about two, or processes. Okay. So looking at the body of the table, right, these ones in the center are joint probabilities, right? So teen going to college and the parents having a degree is 231, right, out of 792. Right. Depends on what you're talking about, what group you're talking about. But in general, right, kid going to college, parents have a degree is 231 out of 792. Going to college where the parent doesn't have a degree, 214 out of 792, right? So those are the ands, right? The joint probabilities in the center there. So we have the probability of C and D. I'll just steal them here. Is 231 out of 792. The probability of C and not D is 214 out of 792. Probability of not C and D, we've talked about some of these already, right, is 49 out of 792. And the probability of not C and not D is 298 out of 792. Right. So we have joint probabilities and then the marginal probabilities on the outskirts. Okay. Let me see your formula sheet. Did I change it to text on there? Great. Thank you. That's one thing I can skip. There's set notation where instead of writing and, this is just a little side note, and is denoted by kind of a horseshoe shape. All right, so I used to go through this. I'll just write it so that you have it just as a note. And or is denoted by a U, right, or an upside down horseshoe if you want. Okay. So if you see those, then that's what they mean. All right. I'll just be using the words and or. It's not that hard to write them out. Right? But if you're writing it out a lot, then it just looks cleaner if you use set notation like this. Okay. Okay. So if we wanted to, right, we just found all these probabilities So we could rewrite our contingency table in terms of the probabilities. So we can rewrite the contingency table as a probability table. So I'm going to say that here I have college, not college, and a degree and not a degree. And on the outskirts, I have totals, total and total. Okay. So I've pre-calculated these. So I'm just going to steal them from here. So 0.29, so to 2 decimal places, we have C and D is 0.29. C and not D is 0.27. And the total is 0.56. Notice, right, that those probabilities have to add up to the marginal probability. Right? Just like the number of people in each of those categories have to add up to the total. Right? And then we have 0.06 and 0.38. Same thing, those add up to 0.44. And the totals for D is 0.35. And the total for not D is 0.65. And then the final total, regardless of which marginals you look at, right? 0.56 plus 0.44 is 1, 0.35 plus 0.65 is also 1. So the total is 1. And I'll just make a note here. Notice that the joint probabilities add to the respective marginal probabilities. Okay. So I'll just skip straight to the definition because you have it on your formula sheet, right? The probability of A given B, we can calculate it, right? If we don't have the table and we can't figure it out, right, then we could calculate it by finding the probability of A and B divided by the probability of B. Okay. So by definition, the conditional probability of the outcome of interest A given condition B is computed by, oops, oh, things got sloppy. The probability of A given B, oops, given C, no, just in general, right? Probability of A given B is the same as the probability of A and B over the probability of B. So I just think of it as the first, so the two events together, right? A and B over the given event, right? The probability of B. Okay. If you had to, right, we can solve for the probability of A and B. Right? I'll just highlight this guy because we're going to use it later. We can solve for the probability of A and B, right, by multiplying both sides by probability of B. So then we have the probability of A and B is the probability of A given B times the probability of B. So this is the general multiplication rule. This is the general multiplication rule. Meaning, if you have to calculate probability of A and B, right, we can't use the probability of A times the probability of B, because that's only true if they're independent, right? If they're not independent, then you have to find the probability of A given B times the probability of B, right? But remember, if A and B are independent, right, then the probability of A given B is just the probability of A. Remember, by definition of independence, knowing the outcome of one, so knowing what happened in B, doesn't affect the probability of A, right? That's the definition of independence. So if A and B are independent, then the probability of A given B is just the probability of A, right? But if they're dependent, or if we don't know if they're independent or not, right, then we have to use this general formula. The probability of A and B is the probability of A given B times the probability of B. We'll stop there, and then we'll start with an example next week. So I'll see you guys on Friday for the lab.
So just to clarify, there's no hand in lab one, right? No. Is there anything that almost like started around lab 2? Like, is there anything on there?
No, not yet. Yeah. Cool. See you guys later.